Chapter 4, Storage Type of Hydropower Projects. 4.1 General Layout of Components in a Typical Storage Power Plant, Dam Body, Spillway, Bottom Outlets, or Under Sluices, Intakes with Examples. 4.1.1 Components of Typical Storage Power Plant. Dam is the principal component of storage plant. It is the barrier built across the river for the accumulation of water on the upstream side. Reservoir. The main purpose of reservoir is to store water during rainy season and supply the same water during the dry season, and thus it helps in supplying water to the turbines according to the load. Intake. It is a structure to divert water into the conduit leading to the power plant. Trash rack screen is provided to prevent the entry of floating debris and coarse bed load into the water conveyance system. It is well equipped with control gate to regulate flow down the conveyance system. Headrace conveyance. Headrace conveyance is the system to carry water from intake to forebay. The conveyance system may be consisting of pipe or tunnel or open channel. Surge tank. Surge tank is generally a cylindrical storage reservoir which is connected to a penstock pipe as much close to the turbine as possible. The main function of surge tank is to protect the long pressure tunnel and penstock pipe from high water hammer effect caused due to sudden acceptance and rejection of load. Forebay. It is structure located at the beginning of the penstock pipe. It supplies the required flow to the turbine during startup, accommodate the rejected flow during shutdown, and 49. Reduce water hammer effect. The forebay is equipped with trash rack to prevent floating debris into the penstock. It also serves as secondary settling basin. Penstock. It is the pipe that conveys the flow from the forebay or surge tank to the turbine. They are designed to carry water to the turbines with the least possible loss of head. Anchor blocks are provided to stabilize force acting on the penstock pipe. Powerhouse. It is the structure where all the equipment for providing electricity is suitably arranged. Tailrace. It is the structure to dispose the water after being used at the powerhouse for the power generation. 4.1.2 General Layout of Components of Typical Storage Hydropower Plant. Typical plan and section of storage power plant. 50. 4.2 Dams and their appurtenant works. Dam is an obstruction or a barrier built across a stream or a river to raise the water level or to store water at the upstream side in the form of reservoir or pond or a lake. 4.2.1 Classification based on function, material, head, and mode of structural load transfer. Classification of dam based on function. Storage dam. Such a dam is used to store surplus water during rainy season to be used later during the period of deficit supply, dry season. The stored water is generally used for water supply and irrigation, fish farming, navigation, recreation, and electricity production, etc. Diversion dam. It is used to raise water level in order to feed an off-taking canal or some other conveyance systems. Mainly used in irrigation and in simple RR-type hydropower development. These types of retaining structures are called weir or barrage. Detention dam. This dam is designed to detain flood water temporarily so as to retard flood runoff to minimize the flood effects in downstream. Detention dams are also constructed to trap sediment and big boulders or cobbles carried by flood water known as debris. Coffered dam. It is a temporary dam constructed to facilitate construction activity. It is an enclosure constructed around the construction site to exclude water so that the construction can be carried out in dry. Classification based on head. Low head dam. H less than or equal to 15 m. Medium head dam. H equals 15 m to 70 m. High head dam. H equals 71 m to 250 m. Very high head dam. H greater than 250 m. Classification based on hydraulic regime. Overflow dam. 51. It is designed to flow surplus water over their crest. The portion of the crest through which excess water flows down is called spillways. The spillway should be eroded-free and capable to pass extreme design flood discharge. Gated overflow dam have controlled mechanism to regulate the spillway flood, while the non-overflow dam do not have any control mechanism to spill out flood discharge. Such a dam is constructed with rigid material like concrete or masonry. Non-overflow dam. It may be provided for entire length if separate spillway is provided nearby. Such a dam can be built by rigid as well as non-rigid material. Classification based on material of construction. Earthen dam is suitable where the foundation is not strong enough to bear the weight of the concrete dam. Earth is used as construction materials and filled up in layers by layers after proper rolling and compaction at optimum moisture content. The seepage through the dam or its foundations is major critical problem in earthen dam. Rock-filled dam. Rock-filled dams are formed of loose rocks and boulders piled in the riverbed by interlocking each other. A slab of the reinforced concrete is often laid across the upstream face of the rock-filled dam to make it watertight. Example: Salt Spring Dam, 345 feet high, in California, USA. Cougar Dam, 445 feet high, on Mcenes River in USA. Concrete dam. These are generally built where riverbed foundations are strong enough to bear the great weight of the dam. Concrete dams are expensive to build but more durable and maintenance-free than the rock and earth-filled dams. Solid masonry concrete gravity dam do not have any cavity or void within the dam body, while the hollow masonry concrete gravity dam contains large cavity or voids up to 35% to 40% to reduce the volume of concrete or masonry. The RCC slab deck, arches etc. are built within the dam body to share the weight of water and overburden weight of the dam itself. It needs skilled labor in complex structures and their design. Steel dam. The steel dams are generally used as temporary or coffer dam. The steel are used to reinforce the earthen or rock-filled dam for strength and impermeability. 52. Timber dam. Wooden flank, post and bamboos are used to construct low-head dam or where creating low-level pool, especially for irrigation of agriculture land, are called timber dam. They have comparatively short life. Classification based on design principle. Rigid dam. Whole body of the dam acts as a single body and dam materials are bonded together with strong bond. Gravity dam. Water thrust is resisted by gravity action. Arch dam. Water thrust is resisted by arch action. Buttress dam. Water thrust is resisted by the buttresses, i.e. inclined structural members to support the load/water thrust. Non-rigid or embankment dam. The earth's fill and rock-fill dams consist of discrete unbounded particles, and the action of seepage through the body of the dam is to be checked besides the slope failure of the dams. Non-rigid dams have capacities to adjust the post-construction settlements and foundation strata, so more applicable in weak foundation zone. 4.2.2 Forces acting on dams and their combination loads on gravity dam. For analyzing the structural stability of dam, following force has to be taken into consideration. Self-weight of dam, W. 53. Hydrostatic load, P. Uplift pressure due to subsoil flow, U. Wind and wave forces, PW. Earthquake forces, P. Silt pressure due to deposited silt in the reservoir, PS. Pressure due to ice formation at water surface, Pi. For analyzing the structural stability of dam, individual above-mentioned loads have to be classified into consideration of the relatively importance of the loads are as follows. Primary loads, secondary loads, exceptional loads. Primary loads are identified as universally applicable and of prime importance to all dams, irrespective of type, e.g. water, and related seepage loads, self-weight loads etc. Secondary loads are generally discretionary and of lesser magnitude or are of major importance only to certain types of dams, e.g. sediment load, thermal load, ice load, hydrostatic wave load etc. Exceptional loads are so designed on the basis of limited applicability or having a low probability of occurrence, e.g. tectonic effect or inertia loads, seismic loads etc. 54. Different loads in gravity dam. Primary load: horizontal forces acting at the dam body of unit length. Water load due to hydrostatic pressures, pH and pH are gamma H and gamma H. Vertical forces acting at the dam body of unit length. Water load: the resultant vertical force, PV, must also be accounted for. If the upstream face has a batter or flare, PV equals gamma asterisk area of the water supported by the flare, and acts through the centroid of area. The pressure of permanent tailwater, PV, equals gamma asterisk area of the water supported by the downstream flare, and acts through the centroid of area. Self-weight load structure: self-weight is accounted for terms of its resultant, W, which is considered to act through the centroid of the cross-sectional area AP of the dam profile. W equals gamma AP, or gamma minus unit weight of concrete. 55. Seepage and uplift pressure uplift force, U, is represented by the resultant effective vertical component's interstitial water pressure. Uplift force is equal to the product of unit weight of water and area of uplift diagram. There are three different possibilities, namely full uplift acting but without tail water, full uplift acting with tail water, uplift acting with drainage gallery. Uplift pressure diagram. The pressure intensity at drainage is usually given by the empirical formula. U equals gamma H plus H minus H. Secondary load horizontal forces acting at the dam body of unit length silt pressure force, pH, equals K asterisk operator gamma asterisk operator H. Where Ka active lateral pressure coefficient equals empty set angle of shearing resistance of the sediment. Value of empty set equals 300, gamma equals gamma minus gamma, where gamma minus sediment's saturated unit weight, value of gamma equals 18 to 20 knots per cubic meter. 56. Hydrodynamic wave load, PW, the transient hydrodynamic thrust generated by wave action against the face of the dam. It is considered only in exceptional cases. It is of relatively small magnitudes. An empirical allowance for wave load may be made by adjusting the static reservoir level used in determining PW. The wave pressure at the reservoir surface PW equals 2 asterisk gamma asterisk operator H, where HW is the wave height. Wave height can be found in the function of the fetch distance, F, and wind velocity, V. This could be calculated through the empirical relationship HW equals 0.0322 square root FV plus 0.763, 0.271 F slash, for F less than or equal to 32 kilometers. HW equals 0.0322 square root FV, for F greater than or equal to 32 kilometers, where V velocity of wind in km slash HR. Typical components of wave formation. The height of the wave is divided in two parts. The above part is the 2/3 of the HW and the lower part is 1/3 of HW with respect to the still water level. Vertical forces acting at the dam body of unit length, silt vertical pressure force, P, equals weight of silt asterisk K, but in actual, silt deposition is not of the isotropic in nature, so the analysis is done with the assumption of the equivalent liquid of the sediment and water mixture. In case of the vertical calculation, gamma is taken to be 1925 kgf/m3, and for the horizontal load calculation gamma liquid is taken 1360 kgf/m3. 57. Exceptional load horizontal forces acting at the dam body of unit length, earthquake pressure developed in the dam itself, P horizontal force due to hydrodynamic load on the mass of dam is given by the relation P equals plus or minus alpha asterisk operator W. Value of alpha equals 0.6 to 0.8 W, self-weight of the dam. Vertical forces acting at the dam body of unit length, earthquake pressure from the water body, P the resultant vertical hydrodynamic load, P, effective above an upstream face batter or flare may be accounted for by application of the appropriate seismic coefficient to vertical water load P. It is considered to act through the centroid of area A1. P equals plus or minus alpha P. Earthquake pressure developed in the dam itself, P vertical force due to hydrodynamic load on the mass of dam is given by the relation P equals plus or minus alpha asterisk operator W. Value of alpha is generally taken about a W, self-weight of the dam. Load combination for gravity dam combination I, dam completed but no water in reservoir and no tail water known as construction condition combination 2, full reservoir level, normal dry weather tail water level, normal uplift, ice and silt if applicable known as normal operating condition. Combination 3, reservoir at max flood water level, all gates open, tailwater at flood elevation, normal uplift and silt, if applicable. This is known as flood discharge condition combination 4, combination with earthquake consideration combination V, combination 2 with earthquake but no ice combination 6, combination 3 with extreme uplift, i.e. drains inoperative, combination 7, combination V with extreme uplift, i.e. drains inoperative. 4.2.3 Site selection for dams and selection of type of dam. 58. Site selection for dam. Dam is a huge structure built on river valley. It requires lots of fund. Care should be taken while selecting site. Wrong selection of site may lead to excessive cost and difficulty in construction and operation. Factors to be considered are: topographical factor. Dam is suitable at neck of river valley where river is narrow and valley which has large storage capacity on the upstream side. Dam is to be located below the confluence of the rivers to take advantages of both the river valleys and flow. High head dam of concrete gravity, arch, buttress and rock fill dams are used for storage. Dam. Geological factors. Foundations having sound rock and river bed. Concrete gravity dams are preferable whereas arch dam is more preferable when foundation is not so strong but abutments are good to take up thrust. For weak geological conditions and river bed and bank where load of concrete gravity dam cannot bear by the foundation and likely to have settlement, the non-rigid dams like earth fill or rock fill dams are suitable. Accessibility. Dam site should be easily accessible. It economizes the transportation cost of construction material, equipment and manpower required which highly reduces the construction cost of dam. Sociological factors. Land inundated by the reservoir after the dam construction also affects the economy of the dam. Resettlement and rehabilitation cost is more for reservoir and dam construction, so the dam should be located in such a place where it minimizes the adverse impacts to the society. Catastrophic hazards that might produce due to dam failure and heavy earthquake also need to consider for dam construction. Availability of construction material and skilled laborers. The dam construction needs lot of construction materials and skilled and unskilled labor force. Construction of concrete gravity dam needs cement, sand, skilled manpowers and sophisticated construction equipments, batching plant, testing equipment etc. 4.2.4 Principal variant of embankment in concrete dams. Principal variant of modern concrete dams. 59. Gravity dam. Gravity dam. Resist pressure and other forces due to its own weight. It is usually made of cement concrete and straight in plan. The shape of the dam is approximating triangular in cross-section with its apex at top. Advantages of gravity dam: strong, stable and durable, quite suitable for wide valleys and gorges having step slopes where earthen dam might slip if constructed, well adapted for use as an overflow spillway section. Earthen dam cannot be used as an overflow section, but even in the earthen dam overflow section is usually a gravity dam. Easily suited to such area where there is heavy downpour since slopes of the earthen dam might be washed out in such area. Maintenance cost is low. Disadvantages of gravity dam: can only be constructed in sound rock foundation. Initial cost is generally higher than earthen dam, takes longer time in construction, more skilled manpower is required. Examples of concrete dam are Calagandakie, 43 m, Camellia, 54 m, and Middlemarciangdi HEP, 52 m. 60. Arch dam. Arch dam. It is curved in plan with its convexity towards the upstream side. It transfers the water pressure and other forces mainly to the abutment by arch action. It is suitable in narrow canyon with steep abutments, flanks, and section is triangular and comparatively thinner. There may be single or double curvature in vertical plane. It is subjected to large stress because of changes in temperature, shrinkage of concrete and yielding of the abutment. Advantages of arch dam: requires less concrete as compared to gravity dam since concrete section is thinner. More suited to narrow V-shaped valley with steep slopes. Uplift is not an important factor in the design of arch dam because the arch dam has very less width and the reduction in weight due to uplift doesn't affect the stability. It can be constructed on a relatively less strong foundation because a small part of load is transferred to the base, whereas in gravity dam full load is transferred to the base. 61. Disadvantages of arch dam: arch dam requires good rock and abutment to resist thrust because if abutment yields, extra stress is developed which may cause failure of the dam. It requires sophisticated formwork, skilled labor, and richer concrete. Speed of construction is slow. Examples of arch dam are Xilidu Dam of China, 285.5 m, Shawan Dam, 292 m, and Hoover Dam, 221.46 m. Buttress dam. Buttress dam. It consists of slab with buttress and load is transfer from slab to foundation through buttresses. Advantages of buttress dam: requires less concrete than gravity dam, can be constructed on relatively weak foundation, powerhouse can be housed between the buttress, vertical component of water pressure on the deck prevents the dam against overturning and sliding, failure can be designed to accommodate moderate movements of foundation without serious damage. Disadvantages of buttress dam: requires costlier formwork, reinforcement, and skilled labor. 62. Overall cost is higher than gravity dam because of the thinner slab. Its deterioration may have serious effect on its stability. Examples of buttress dam are Roseland Dam, France; Coolidge Dam, USA; Mount Dell Dam, USA. Principal variant of earthen dams based on method of construction: rolled fill earth dam. In this type of dam, successive layers of moistened earth are laid one after the other. Each layer is laid after the layer of earth previously laid is adequately compacted. Sheepfoot rollers are mostly used for compaction. Rolled fill earth dam. Hydraulic fill earth dam. In this type, construction, excavation, transportation, and placing of the earth is done by hydraulic means. Outer edges are maintained slightly higher than middle part. The mixture of excavated materials with water is pumped and discharged at the outer edges of the dam. No compaction is required in this process. Hydraulic filled dam. Based on section of dam: homogeneous earth dam. This dam is made of single material. The homogeneous dam is made from impervious or semi-pervious soils. Upstream slope is generally kept flat so as to reduce the path or seeping water and to counteract the effect of sudden drawdowns. 63. Homogeneous dam. Zoned earth dam. It is made by using one or more material. The central part of the dam, known as core, is made from impervious material. Relatively more pervious material is used on the both sides of the core. The dam may consist of a rock toe for horizontal drains. Zoned earthen dam. Diaphragm-type earth dam. In this type of dam, the bulk of the embankment is made from pervious soil, but a thin diaphragm of impermeable material is provided at the central part of the dam to check the seepage. The difference in zoned and diaphragm-type earth dams is due to thickness of impervious core only. If the thickness of core is less than 10 m or less than the height of the dam, then it is called diaphragm type. Else it would be zone type. Diaphragm-type earthen dam. Based on material: rock fill dam. 64. This dam is made predominantly from rock boulders. Only boulders can prevent the flow of water through them, and as such some impervious layer is laid on the U/S face of the dam. Rock-filled dam. Earth-filled dam. If the compacted soil accounts for more than 50% of the placed volume of the material, then it is called earth-filled dam. It may be of various types: homogeneous with toe drain, with central core, with transition drain, with inclined core, or with horizontal drainage blanket. Earthen dam with drainage. 65. Combined earth fill and rock fill dam. The downstream portion of the dam is filled with rock and upstream portion is filled with soil with riprap on the slope and reservoir side with cement grouted core wall against seepage. The riprap is formed with cement mortar over stone pitching to make upstream slope stronger for seepage and water erosion. 4.2.5 Failure modes of embankment in concrete dams and their prevention measures: foundation treatment, grouting and their necessity. Failure modes of embankment dam and design principles. The principal defect mechanisms and failure modes identifiable in embankment dams are as follows with schematic diagrams. Hydraulic failure. 40% of failures will be occurred in embankment dam with the causes of hydraulic failure. Hydraulic failures may be occurred due to the following reasons. Overtopping failure. Overtopping failure is occurred due to the flow take place above the crest level due to the various causes, i.e. inadequate flood discharge spillway design, insufficient freeboard, etc. Overtopping leading to washout, less cohesive silts, sands, etc. at greatest short-term risk. Almost 30 to 35% of serious incidents and failures will be occurred due to the internal erosion and overtopping mechanisms. Overtopping leading to washout. 66. Wave erosion. The wave action due to the wind and tides will cause the erosion of dam materials at the upstream face, if the dam materials could not sustain wave velocity. It will lead to washing out of the dam material or overturning of the protective materials over the upstream side of embankment dam. C. Toe erosion. Toe erosion may be occurred due to the flood discharge by the causes of the badly designed of the spillway channel. Downstream slope erosion may be influenced by the downstream water. D. Surface erosion of the downstream slope. Due to the heavy rainfall intensity, downstream slope may be eroded and may form the several gullies along its slope direction. Ultimately, serious damage to the dam may occur with long duration of rainfall. Seepage failure. Almost 30% of failure will be occurred due to the seepage failure, which can be examined by past experiences. Seepage failure may be categorized as follows. A. Piping failure. If the exit gradient of the seepage flow is more than the critical gradient of the soil, then soil particles are susceptible, easily influenced, for the dislocation. As the surface particles are dislocated, then process will be even accelerated towards the downstream direction because seepage gradient will further increase continuously. Internal erosion in piping are formed with migration of fines from cores or slash and in foundation or slash and particles from body due to the formation of internal cavities. Internal erosion in piping with migration of fines from core and in foundation. B. Sloughing. If the seepage line, top phreatic line, exists at the downstream face of the dam, the portion of toe of the dam below the exit point will always in the saturated condition. It will cause the reduction of the stability of the slope and slowly sliding may occur. Due to the phenomenon of the repetition of the wetting and sliding, the dam leads to failure. This phenomenon is called sloughing. 67. Downstream slope failure by sloughing, reducing shear strength of materials. Structural failure. Almost 30% of failure will be occurred due to the structural failure. Structural failures are due to a. Failure due to the poor water pressure. If the poor water presenting during the construction on the embankment body of the dam, then much of the stress will be resisted by the water itself and effective overburden pressure on the soil will be less. This poor water pressure will be reduced the shear strength of the soil of the body and may cause the failure of the embankment slope due to small shearing load on the dam body. B. Downstream slope failure. At seepage of water through the body may be maximum rated maximum level of water on the reservoir, then downstream slope are more vulnerable to slide due to seepage force along the driving force for the sliding. C. Foundation slide. If the foundation of the dam is formed on the soft soil and or slow consolidation and expansion of clay soil due to saturation process will reduce the shear strength of the foundation soil. It may not be able to resist the shear stress induced by the embankment. At this condition, the dam body as a whole may slide. Failure of D/S foundation due to overstress. D. Sudden drawdown on the upstream. The sudden drawdown of the reservoir will cause the seepage force acting along the sliding direction, causing increase of the driving force for slope failure. 68. U/S slope failure by rapid drawdown of water. E. Failure due to leaching of soluble salts. Large cavities inside the body of dam will be formed due to the leaching of the soluble salt, iron oxide, calcium carbonate, on the embankment dam body as well as in foundation, resulting to the excessive settlement of the dam. Embankment and foundation settlement. F. Due to earthquake. Due to earthquake, cracks may be formed at the impervious layer and arising the piping and leakage problem on the dam. Also, excess settlement problem, overtopping, increasing pore water pressure due to liquefaction and sliding of the surrounding mass into the reservoir problems may be raised due to the earthquake. G. Failure due to spreading. H. Failure due to grazing of animals. Modes of failure of concrete dam. The various modes of failure of concrete dam are as follows. Overturning. Various forces act on the dam. Some forces produce clockwise moment about the toe while some produce anti-clockwise moment. Clockwise moment tries to overturn the dam about toe while anti-clockwise moment resists it. Thus, overturning of concrete dam takes places when clockwise moment is greater than anti-clockwise moment. Thus, a factor of safety against overturning is maintained to avoid the failure of dam by overturning. Factor of safety against overturning equals resisting moment. Overturning moment equals mm. 69. Fs against overturning greater than 1.25, low but acceptable. Fs against overturning greater than 1.5, desirable. Sliding. The dam body may fail by sliding over foundation or any other section. Generally, the critical section being at the foundation, we check the failure of dam by sliding at the base. The force that tries to slide the whole dam is the net horizontal force. And the force that resists sliding is the frictional force between dam and the foundation. Frictional force, F, equals mu sigma V here, mu equals coefficient of friction equals tan phi equals angle of repose equals angle of friction, hence, sliding factor equals mu, sigma V, sigma H greater than 1. In case additional shear resistance between sliding surfaces is considered, the factor is called shear friction factor, equals sigma 4.5. Here, Q is the shear resistance between surfaces due to joints. B equals base width of dam. Compression failure / crushing failure. Compression or crushing failure occurs when the compressive stress in the dam foundation or dam material exceeds the permissible compressive stress in dam or dam material. This is obtained by stress analysis of dam, which is discussed later. Tension failure. We know that concrete is weak in tension. Whenever tensile force occurs in the dam, the tension cracks develop, which enhances seepage and hence stability of dam is reduced. So it is tried to avoid tension force at any section of dam. For no tension to occur in the dam, the resultant should lie inside 1/3 of the dam from the toe. This rule in dam stress analysis is called middle third rule, which is discussed later in detail. Foundation treatment. The foundation of dam must be strong enough to withstand the foundation pressure exerted on it, as entire load acting on the dam are ultimately transmitted to the foundation. So, it should 70. Consist of solid and sound rock. But in actual practice such an ideal foundation is not available. Therefore it is necessary to carry out geological investigation to determine the suitability of the foundation for the dam. If defects are observed, the suitable measures can be adopted. Foundation treatment commonly adopted for all foundation is carried out in 3 steps. Preparing the surface. Grouting the foundation. Foundation drainage. Preparing the surface. It consists of removal of entire loose rock, soil, till a sound bed rock is exposed. The excavation of loose rock laying over the bedrock should be carried out carefully, so as not damage the bedrock. The final surface obtained above is stepped or made rough to increase the frictional resistance of the dam against sliding. Preparing to surface. Grouting the foundation. It consists of drilling deep holes into the foundation and injecting a mixture of cement / water, called grout, into the holes. Grouting is required to seal the cracks and fissure in the foundation for improving the bearing capacity of the rock and reducing the uplift pressure. The primary purpose of the grouting is to form a continuous watertight curtain at the U/S heel of the dam and to eliminate or minimize leakage of water under the dam by increasing the leakage path. The foundation grouting is usually of 2 types. They are consolidation grouting and curtain grouting. Consolidation grouting. It improves the characteristics of the foundation rock and increases its strength. The entire base area of the dam is consolidated by grouting. Shallow holes, BHOs, are drilled through the foundation rock. The depth of the hole is between 3 to 15 m, spacing about 12 to 30 m and diameter 5 to 10 centimeters. After the holes have been drilled, a mixture of cement slurry, 1:3 to 1:8. 71. Is forced into the holes at low pressure of 3 to 4 kgf/cm2. Consistency of grout depends upon the water tightness of the rock. After grouting these holes, secondary holes are drilled to 1/2 to 2/3 of this depth and grouted. If the foundation rock is poor, tertiary holes are drilled and all are made as deep as primaries. Consolidation grouting. Curtain grouting. Curtain grouting. For high-pressure grouting is done to form a deep curtain wall or an impervious barrier in the foundation just D/S of the heel of the dam. The main purpose of curtain grout is to reduce uplift pressure on the dam. It also helps in reducing seepage through the foundation. Holes required for curtain grout are quite deep. The depth of hole depends on the nature of the rock and the height of the dam. The depth of the hole is generally taken 30 to 40% of the depth of water in the reservoir for strong foundation and maybe as much as 70% of the depth of water for poor rock. The primary series of hole in a line is usually drilled first, having spacing of 4.5 to 7.5 m. It depends on the nature of rock and grouted under high pressure. Then secondary series of holes are drilled between the primary holes and grouted. Sometimes additional tertiary holes are also drilled between primary and secondary and grouted. Generally, grouting pressure is about 0.25 d/kgf/cm2. Where DO depth of grouting in meter below the surface. Curtain grouting is generally carried out in stage in depth of about 15 m in one stage. As the grouting pressure is very high, curtain grouting is carried out from galleries only after some height of the dam had been constructed to avoid lifting up or dislocation of the foundation strata due to high pressure. 72. Curtain grouting. Foundation drainage grouting system usually reduces the uplift on the dam and the seepage through the foundation. However, it is impossible to provide absolutely perfect impervious barriers. So to remove the seepage water through the foundation, drainage system is usually provided D/S of the curtain grout. It consists of a series of holes drilled in one row to a depth varying from 20 to 40% of the depth of water in the reservoir in spacing between 1.5 to 2 m. The drainage holes are connected to the drainage gallery to drainage seepage water. 4.2.6 Design of gravity, concrete, dams, general considerations, cross-sectional profiles, stability analysis, safety factor against overturning, sliding, stress and material failure, crushing, limiting height of concrete dam. Design criteria of gravity dam. The essential criteria governing the structural competence of a gravity dam follow from consideration of equations sigma h equals 0, sigma v equals 0 and sigma m equals 0. The criteria for structural analysis of gravity dam are as follows: rotation and overturning, translation and sliding over, stress and material failure. Overturning and sliding controls, overall structural stability. The sliding criterion is generally the most critical of the above three. 73. Overturning stability factor of safety with respect to overturning, FO, can be defined as the ratio of the summation of all restoring, i.e. positive, moment, sigma m plus v, to the summation of all overturning moment, sigma mv. Thus, FO equals sigma greater than 1.5. Value of FO in excess of 1.25 may generally be regarded as acceptable. But FO 1.5 is desirable. Determination of a value for FO is not universal practice owing to the link between overturning moments and stress level. Adequate stability in relation to overturning may be assured by specifying limiting stress levels for concrete, e.g. no tension. Sliding stability sliding factor, FSS, it is expressed as a function of the resistance to simple sliding over the plane considered. It is assumed that resistance is purely frictional, and no shear strength or cohesion can be mobilized. Sliding factor can then be defined as the ratio of the summation of all horizontal load components, sigma h, to the summation of all vertical loads, sigma v, on the plane considered, i.e. for a horizontal plane. FSS equals sigma 1. Shear friction factor, FSF. FSF is defined as the ratio of the total resistance to shear and sliding which can be mobilized on a plane to the total horizontal load. i.e. FSF equals sigma empty set sigma 4 to 5. Middle third rule. Let take the section AB on the dam body. Length of the dam along the transverse direction of the fig is taken to be unity. If R is the resultant force of all forces acting on the dam body above the section AB. RH and RV are horizontal and vertical component of resultant force. Let normal stress sigma equals asterisk operator bending moment M will be developed at the considered section is CM equals RV asterisk E. Bending stress developed at any point Y along the AB where Y is taken from point O. 74. Sigma equals asterisk operator. Where Y equals and I equals asterisk operator, the resultant normal stress of the both stresses. Sigma equals sigma plus or minus sigma. Equals plus or minus asterisk operator. Equals plus or minus asterisk operator. Equals 1 plus or minus asterisk operator. Note: when the reservoir is full, maximum stress occurs at equals sigma. Diagram of compressive and tensile stress. Note, if sigma then sigma will be plus, i.e. compressive stress will be developed everywhere. Sigma equals sigma, then tensile stress value will equal to 0 when E equals plus or minus limiting case. Sigma sigma, then sigma will be, i.e. tensile stress, value, will be developed. In limiting case, no tensile stress at all, for both the case of eccentricity left or right of O0 equals 1 plus or minus, this will prevail when E equals plus or minus. Principal and shear stresses in a gravity dam. Principal and shear stresses at toe. Consider small triangular element def at the toe having unit length DE and DF are the principal planes subjected to principal stress in PE. The plane EF part of base of the dam subjected to vertical stress and shear stress. Let dx, ds and dr are the length of side EF, DF, ABD, DE respectively, be the angle made by the downstream face with vertical. Now considering triangular element is in equilibrium. 76. Stresses at toe. If there is no tail water, P equals PE equals 0. Then, sigma equals FSEC 2 theta. Principal and shear stresses at heel. Consider a small triangular element ABC on the U/S side at heel. The plane AB and AC are subjected to principal P and sigma equals the plane BC part of base of dam subjected to a vertical stresses F and shear stress tau. Let dx, dr, and ds are the length of the side BC, AC and AB respectively, and theta be the angle made by the upstream face with vertical. Now considering element is in equilibrium. Stresses at U/S. (78) For reservoir empty condition force, P equals 0. 78. For reservoir empty condition force, P equals 0. Tau equals F tan theta. Sigma V equals 0. 78. 78. For reservoir empty condition force, P equals 0. Tau equals F tan theta. Sigma V equals 0. P ds sine theta sigma dr cosine theta plus F dx equals 0. Or, P dx sine theta sigma dx cosine theta plus F dx equals 0. Or, P sine 2 theta sigma cosine 2 theta plus F equals 0. Or, sigma cos 2 theta equals phi u, P sin 2 theta. Therefore sigma equals FSEC 2 theta, P tan 2 theta. Considering earthquake forces. Sigma equals FSEC 2 theta, P plus P, tan 2 theta. For reservoir empty condition, P equals 0. Sigma equals FSEC 2 theta. Elementary profile of a gravity dam. Elementary profile has no top width and no freeboard. It is right-angled triangle with its apex at the water surface. It is an approximate shape of gravity dam which gives an insight into the design of gravity dam. Elementary profile of a gravity dam. No tension basis. For no tension basis, resultant force R must pass through the middle third of the base. In such case, maximum value of eccentricity E will be B/6 when it passes through the point A. When the resultant passes through point A, the sum of moment of all the forces about A equals 0, sigma M equals 0. Or, W P U equals 0. Or, BHG gamma H to gamma K. #81. Therefore, sigma U equals 0 shear stress, at toe, tau equals, F, P, tan OD equals gamma asterisk H square root G minus K. At heel, tau equals, F, P plus P, tan OU equals 0. For the reservoir empty condition vertical stress, at heel, F equals 1 plus. As, V equals W equals 82. Central core of dam, width of core at top is usually 0.8 to The phreatic line can be located either with graphical or analytical or experimental methods. Graphical method. The procedure for graphically construction of the phreatic line is as follows. Flow net with drain. BC equals is an element of H. Equals 0.40. AB is the U/S face. Let its horizontal projection be L. BC equals 0.3 L. The point C is the starting point of base parabola. To locate the position of the directrix of the parabola, the principle that any point on the parabola is equidistant from the focus as well as directrix. Hence, with the point C as the center and CF as the radius, draw an arc to cut the horizontal line CB and D. Draw a vertical tangent to the curve FD at D, CD equals CF, hence the vertical line DH is the directrix. The last point G on the parabola will lies midway between F and H. In order to locate the intermediate point on the parabola, FP equals PI, draw vertical line QP at any distance x from F and measure distance QH with F as a center and QH as a radius. Draw an arc to cut the vertical line through Q in point P. Join all these points to get the base parabola, however correction is to be made at the entry point. 85. Calculation of the seepage discharge through the dam with horizontal drain. In order to find the equation of the base parabola, consider any point P, X, Y, W. Or T to focus F. '89. Case 3, seepage discharge for the dam with phreatic line emerging at the downstream face of the dam if there is no downstream water. From the continuity equation, K, increment asterisk operator, equals increment 1 plus 2.3 log increment. For H equals 0 then, or, increment asterisk operator, equals increment, 1 plus 2.3 log increment. Or, increment asterisk operator, equals increment or, H minus increment equals increment, 2, L minus increment M. Or, increment plus H equals 0. Or, equals plus or minus 4H. Or, equals plus or minus H. Equals plus or minus H. The locations of the emerging of phreatic line are important because of the location of phreatic line inside the dam body will help in finding the seepage discharge through the dam and finding the water pressure any point inside the dam body. The demarcation line of the saturated and dry soil, which is used to calculation of specific weight of soil mass for stability analysis. It is required to check the possible failure of the dam by sloughing or other process of failure. 4.3 Intake. It is a hydraulic structure constructed at the head of an irrigation canal, tunnel conduit, or power canal to obtain the required quantity of water from the river or reservoir for the different engineering purposes. 4.3.1 Purposes of intake. The main purposes of intake structure as a regulating structure are follows: to admit and regulate water from the source and possibly to meter the flow rate. To control the sediment entry into canal, to admit smooth, easy, and turbulence-free entry of water into the canal. 90. To prevent the clogging of the entrance with floating debris. The following are major appurtenances of the intake structure: the raised inlet. Thank you.